So we went over KA problems, 3 types of problems that resemble the 3 types of Unit 7 equilibrium problems. We left off with the 3rd type, and you guys are supposed to do, what the heckaroonie? Shut it. Okay, it's too late for Cole. He needs to listen now in class. And you have things you have to do in the back called make an answer key. Finish the PowerPoint slide and make an answer key. Oh. So, okay. So we left off with a practice opportunity. Okay. And now what today is I move some things around and we're going to finish up KB problems, which should actually go pretty quick because they're just kind of a mimic of KA problems. Just adding one extra step of relating KA and KB through relationships, right? Mathematical relationships. And then I move things around so you will not have a test until I think Wednesday or Tuesday of the week after Thanksgiving. And you will also have a lab, okay, when you come back. But I'm trying to slow a couple things down for you because it is just such a math heavy unit. I am including now the process in the side. You probably, unless you have decided that math logic is where you want to focus your attention on for example problems, you probably don't have time to write out these steps because some of you guys just need the full problem with numbers for yourselves. Totally fine. Go back. I upload the notes always around 4 p.m.-ish every day. So that's kind of where we're at. You should have followed the steps above. And let me get my cap on. And for this problem, okay, you were given a weak acid, ascorbic acid, which by the way is like in all your sodas. Do you guys remember one of your first titration lab was with ascorbic acid of some sort? It's citric acid, okay? And you're asked to calculate the Ka for this given, okay, the pH is 3 and you have a molarity of the acid. So using the steps above, again, I highly recommend when you write out these equilibrium equations, you don't try to look up the compound. You just do ascorbic, right? Protonated versus deprotonated, right? That is my recommendation. Don't waste your time trying to get the compound correct because in the end, that's not really what liquors. That's not really what matters. Okay. And you should have set up an ice table. Okay. And you were given blah, blah, blah. You were given the initial, which is 0.100. And you know that you start off with nothing. This is not a common ion problem. This is not, I dumped it into solution with this similar ion. There's no contribution. This is, I just started reacting it. What's happening? Hey, what's up? So you should have used your stoichiometric ratios, right, of change. And you can figure out the value of equilibrium for the H3O based on the pH, right? So you should have figured out what was the 10 raised to the pH value. That tells you your equilibrium concentration for H3O. All right. I'm running through this because honestly, this should be very simple for you guys. Okay. And you had the walkthrough above if you were here and you took notes. Okay. And so what did you get for your Ka value when you plugged it into the expression? What was your Ka? Joy. 1.0 times 10 to the negative 3. Okay. Reminder, sig figs. So it looks like we can only have 2 sig figs based on pH. pH tells us there are 2 digits after the decimal. So you can only have a 2 sig fig, Ka. Remember, for these types of problems, since you don't know what Ka is, you cannot use the 5% negligibility assumption. Yes.
Oh, is that -5?
Oh, -5, sorry. Thank you. So be careful not to use negligibility, that 5% ionization rule. It's pretty much only applies to one type of problem. When you're given the initial and you're given Ka, pretty much otherwise you can't use that negligibility because you just don't know what, for the second type of problem, you don't know what the initial is. So you can't determine if it's irrelevant or not, if it's insignificant loss. And then if you don't know Ka, you don't have anything to compare to. So you still can't know. So anyone have any questions on this specifically, given that you do have a walkthrough above? Any questions? Yes, Joy.
For the negligibility one, do you first assume it's negligible? And then if it's not, just go back and do the problem?
No, you wouldn't know. You can't, you never assume it's negligible unless you're given the data, which is Ka and initial concentration. No, you never assume negligible. You can never assume negligible unless you actually have initial concentrations and Ka to compare. What if you do, your value will be wrong?
No, like what if you do have the initial thing?
Then you can compare it to Ka as long as you have Ka.
What's the equation for that?
Like it has to be about 1,000 times 1 times 10 to the 3 powers greater. Your initial has to be 1,000 times greater than your Ka. Essentially, your ionization product constant, how many ions you produce. Ka is just the multiple of the ion concentration that you produce. Okay, so now we're going to head into a paralleled version of this with KB calculations. So yes.
When you say put like shelves,
I want you to reorganize the shelves. I want you to take everything out of the kits and put them on the shelves with a label of like each unit, AP unit, this is the lab it goes with. Like I set up, but I think you need to reorganize the shelves so that it goes correctly. I want to be able to go to the shelf, pick up a kit and transport it. And I need it out of the boxes. Okay, so with KB calculations, we're getting a similar thing, okay? We're seeing a complex calculation due to the fact that we have partial ionization. This is the whole point of these calculations, is that you are in equilibrium. So of course you need to account for the fact that you are undoing yourself as much as fast or with relative consistency of doing yourself, okay? So we assume a reversible reaction and thus a process in equilibrium. Okay, so this day always throws me off. Okay, so for the first type of problem, there is a quick reminder of a quick note that you want to remember to yourself is that the setup for a general base equation, which is base, right, plus water, okay, goes to protonated base and OH minus. Okay, that's our general format. You, of course, then can write the KB expression sub B, which is equal to the concentration of HB plus, because it's been protonated, times the concentration of OH minus ion all over B. Okay, and of course, raised to your stoichiometric coefficients, but generally it's a 1 proton transfer. So you're pretty much with acid-base reactions in terms of titration calculations in Ka and Kb, you almost never see any of these raised to a power. Unless you're dealing with a polyprotic acid, then that's different. But even then, like, yeah. So what will become really important for you guys to remember is when you're doing KB calculations, you'll often be given data in terms of the acid, but they ask you to solve for the base perspective. So you're going to want to remember these following relationships. One, Kw, which is equal to 1.00 times 10 to the negative 14th, is equal to Ka times Kb, which is also equal to, I know this is weird, H3O plus times OH minus. Okay, that's a relationship that you're going to want to know. You're going to use a specific sect of that, okay, however you want to partner that equivalence. You also want to know that pKa plus pKb is equal to 14, which by the way is also equal to POH plus pH. So those are going to be some relationships that you're going to have to consider when you're doing these problems, okay? So problem type 1, we definitely have still a percent ionization that we can apply. As long as the percent ionization is less than 5%, oh my God, 5%, you can assume for problem type 1, assume the change in initial concentration to be negligible. Initial concentration of your base source, negligible. Right? So this is what happens when you 5% less than that. When you divide your OH minus production by your base. Okay. And so that would be like saying your Ka, yeah, your Ka, essentially your Ka divided by your base concentration. If you get 1,000 times difference, You can write it however way that makes sense in your head. If you get 1,000 times different, you know, or more, you know that that change is essentially negligible to the impact of your reactant. And it is only for these type of problems when you're given initial concentration and you're given Ka. You cannot assume this for any other type of problem because it's not safe to assume it. Okay, so here again, I write all of the steps. These tend to be slightly longer because you often are transitioning between acid and base, okay? But for this one, what we do is we have a reaction, okay? And here we have this compound methylamine, and it has a Kb of the following value. Calculate the pH of a 0.5 molar solution of methylamine. So you want to end up in terms of acid, but you're given everything in base, okay? So the first thing that you need to consider is, well, I need to figure out what my concentration of I need to just plug it into the ice table. So I'm going to write my equilibrium for this reaction. I don't know. I would honestly just write methylamine. I don't really want to write the full thing. Plus H2O goes to protonated meth again. I think we talked about protonated meth last time. Methylamine. Okay. And OH minus. Then you set up your ice table.
You did actually add the H to the methylamine.
Yes, it would be the H attached to the N that would be lost. So it would become CH3NH minus would be the conjugate base if you wanted to write out the product. You almost never ever lose H's attached to carbons, like never. Oh, thank you. Yes.
Oh wait, why would we?
Sorry, I didn't mean minus. I meant plus. I'm thinking in terms of acid.
H3.
So it would be CH3NH3 plus. Yep. Okay, sorry, I flipped that in my brain. So you're told initially you have to figure out what the concentration of OH is based off of the POH. Okay. So you're going to use a relationship that POH is equal to 14 minus pH. Do you have headphones? Yep. Which is equal to 14 minus okay, negative log of 0.5 molar. And that's going to get you a value of, can anyone do that math? Wait. Guys, what are you allowing me to do? Wait, why are you allowing me to do any of this? They tell us the concentration. I'm just being an idiot. It's 0.5. Oh my God. You guys need to make me stop talking. You need to make me stop talking. Okay. Okay. So we were told that's why this, hello, guys, your t-shirt is only 25. I have many mistakes publicly that I make them. You need to call me out on them and not let me journey too far in my mistakes. Okay. Because then I get sad about how many mistakes I made. Just cut me off at the knees, okay? Make me even shorter than I am, okay? So we were told that we have a 0.50 solution of this methylamine, okay? So we just do our usual 0, 0, okay? We do our usual algebraic stoichiometric ratios, okay? Minus x, okay? Plus x, okay? And we know that we're going to have pH of 0.5 solution of blah, 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 blah. And yeah, we don't know anything else, basically. Like, that's it. We don't really know anything. So we know it's x, and it's 0.5 minus x, okay? That's what we know. Now, the question is, before we do all this work to put it into our formula, okay? What we need to do is we need to first figure out, is it negligible? Exactly, using KB. So we know that we have 0.5. KB is times 10 to the negative 4. So we can consider this negligible. You would have to show that KB is 1,000 times okay, less than the initial concentration of methylamine. So you know that this is negligible. So it ends up just becoming 0.5, 0.5, X and X. Okay. Now, you need to not actually plug in to KB equation. Oh, no, you do. No, you're going to plug into the KB equation. So you're going to do X squared and you're going to solve for X because that's going to tell you the OH. And if you can find the OH, you can find the pH. There it is. If you can find the OH, you can find the pH. So we have X squared all over 0.5. Okay. And then when you solve for that, you set it equal to 4.4 times 10 to the negative fourth. Okay. And when you set all this equal to, you get that the OH, which is X concentration, is 0.0148 molarity. Okay. Then you just plug this value into POH to find the POH. And if you can find the POH at equilibrium, you can then find the pH of the solution once it's attained equilibrium. So this would become POH, and that would equal 1.829. And if you know pH, you can find, POH, you can find pH. So then it becomes 14 minus 1.829 equals my pH. So my pH is equal to 12.17, which makes sense considering that you are creating a basic solution. So of course, the pH of your overall solution from the acidic point of view is going to be incredibly basic, incredibly high. Okay, so to summarize that first initial train wreck, all right, that you all let me continue to drive the train toward, is you were given the initial, okay, you were given the KB, you plugged in to an ice table what you know that you didn't produce any ions, so you use your stoichiometric ratios to create an algebraic expression between the change and the equilibrium concentrations. Since you have KB and you have initial OH minus, initial base source, you can use the percent negligibility rule. And you do have 1,000, difference, a 1,000-degree difference between the initial and the KB, which tells you that the amount of ion production, it's so small that it barely impacts your initial concentration. So that's why we consider it negligible. It's just not a value worth tracking at this point. It's not significant enough. Then what you do is you plug into your KB because that is the relationship that you're going from. You're going from a base perspective. So you plug into the equilibrium for your base, your production of OH minus, and you solve for X. If you know X, you know OH minus. If you know OH minus, you know POH. And if you know POH, you can use the relationship between pH and POH and the number 14 to find the pH of the overall solution, even though it was given to you from a base perspective. You can still find the acidic perspective. Okay, that's your summary. Try the next one on your own. Go much faster than I did. Yes. All right, so for this one, you should have, hopefully with much more straight line logic than my initial explanation, gone through this problem where you use, just like the other problems we walked through, Ka and unit 7K equilibrium problems, where you're given the initial of the reactant and you're given some form of information, Kb, okay? And you're able to then assume, look for negligibility, and then fill in the chart, create an algebraic expression, and solve. The only additional step here is that you're being asked to switch to the acid perspective given base values, okay? But you should have gotten that, okay? When you looked at this, you were told that you have a initial concentration of 0.2 molar. You probably had to scroll back to that part of your notes where there are the bunch of Ka and Kb values. Now, what you notice is you were given Ka. So you would have had to use another relationship that I defined up here that allows you to find Kb. So that you, in a way, you were technically given Kb because you had to look for Ka on the table. And if you know the Ka of a specific element, you can find its Kb through relationship. So you would say that the Ka, according to the table, for HCN. This is Ka for HCN. Its conjugate acid is equal to 4.9 times 10 to the negative 10th. You then could plug in that KB is equal to KW divided by Ka. So what you would find is that it's 1.00 times 10 to the negative 14th all over 4.9 times 10 to the negative 10th. And you would have found that KB is equal to 2.04 times 10 to the negative 5th. How many of you guys went back to your previous notes, the tables? How many of you guys remembered to go back to that page? Okay, awesome. That's why I told you to bookmark it. Okay, so now you will have your given KB. So now you can, okay, move forward. You know that the change will be an 1-to-1 ratio because that's what we're transferring. Okay. And that leaves you with an equilibrium algebraic value of x, and 0.2 minus x. Now the question is, am I a more than 1,000 times smaller Ka value, more than 1,000 times smaller in ion production than I am in initial concentration? And the answer is heck to the yes. Okay, you're more than 10,000 times difference. So you know that this is going to be negligible. It doesn't actually matter in the end. So then what you do is you set up your equilibrium. When you say, well, KB is equal to this, and I know that that means equilibrium expression wise, that's equal to the concentration of HCN conjugate acid and OH minus hydroxide ion multiplied together, x times x is x squared, all over 0.2. You solve for x and you get that x is equal to 0.00202 about, which is, by the way, equal to the concentration of OH minus at equilibrium. You're asked to find the concentration, the pH of the solution at equilibrium. Unless they tell you it's specifically at initial conditions, you know that you're talking about pH at equilibrium. So what you then do is you just plug into pH equals 14 minus POH, right? Which you can easily solve, and you get that the pH is equal to 11.31. And notice, this is a 2 sig fig value. You have to report to the second digit because you were given a 2 sig fig initial. Any questions with this one? And don't forget, if you're like, whoa, okay, you can go back, look at the process, find each step in this write out. Okay. So that's the essential step. And I think for here, I'm going to modify the step to say, instead of Ka from the table, you might have to find Kb from Ka. From Ka. You might have to do Kb from Ka. It was a nice modification, unless they give it to you directly. Okay. So second type of problem. Okay. This time you need to figure out the initial, and you're given Kb and pH or POH at equilibrium. So what you know here is really important. What can you never apply with this type of question then? Yeah, the percent ionization is negligibility. Percent ionization negligibility rule is just not a thing. It's just like a big no. Okay, no, don't do it. You can't make that assumption safely. So for this one, okay, you follow a pretty similar process, okay? And what you have here is we have the concentration. What concentration of NH3 would be required initial to produce a solution with a pH of 10.5? So if you know pH, all right, you know this is the pH at equilibrium, okay? This is at equilibrium. If you know pH at equilibrium, you can solve for POH at equilibrium. And if you can solve for POH at equilibrium, you can solve for the concentration of OH minus at equilibrium. So you do a little floop-de-doop, okay, of the relationship, and you get that the concentration, right? You'd solve for POH at equilibrium, okay, through 14 minus pH. And then you would get what? That equals 3.50, 2 sig figs. And then you say that OH concentration at equilibrium is equal to 10 raised to the negative POH. So you'd get a value of 3.16 times 10 to the negative fourth molarity. Okay. So that would be the first step is, okay, figure out where my equilibrium status is. Because if I know one value of concentration equilibrium, I can use stoichiometric ratios to figure out the other values. Okay, now that we figured that out, let's go ahead and write out our equation and set up our ice table. We could also just jump straight to also knowing KB. So given KB, again, you would probably be giving it in the prompt, but for this, you would actually have to look up. Well, let me write out the equation. I think that would help better. So we have NH3 reacts with H2O, and here water is the better acid. So we get it's an equilibrium with NH4 plus ammonia production and OH minus, okay? And you set up your ice table, and you need to figure out what the KB is for this. But the problem is you aren't ever really given KB, especially when it comes to table data. We do everything from the A perspective, the acid perspective. So you need to look at the Ka for NH4 plus. And you know, when you look at the table, that that's going to be 5.6 times 10 to the negative 10th. Pretty darn low. Okay. And you know that then if you know this, that KB has to equal KW over KA. This is just a mathematical relationship that you manipulate. Don't ask me how I derived it. Don't ask me. I am not a derivation person. I am a, here is the equation. This is how you conceptually make sense of it. Please use it correctly. That is you. This is the type of teacher you have when it comes to those math questions. So then you plug in to solve for KB. So it essentially KB is given, granted that you do a little bit of work. Okay, and you get that KW 1 times 10 to the negative 14th all over 5.6 times 10 to the negative 10. Okay, and you would get that KB is equal to 1.78 times 10 to the negative 5th. Okay, oh, that looks like a 3. Oh dear. Times 10 to the negative 5th. Okay, now that you know that, you actually can do, that's it. So you're gonna now start filling in your table, okay? You need to solve for X. Here, X is your initial. Obviously, the water does not matter. Obviously, you start with nothing. This is not a common ion problem, so you never mess with it, okay? You just assume 0. You're just starting out this reaction, okay? You're just starting up this mixture. And you take, okay, your equilibrium value that you found, copy, and you say paste. Okay, I know that's the equilibrium concentration for OH. If that's the equilibrium concentration for OH, that means this must be the equilibrium concentration for NH because I change in a 1-to-1-to-1 ratio. I lose and I produce in a 1-to-1 ratio. Okay. And I'm just going to add in my pluses and minuses for the change, just so it stands out. Minus, a plus, and I get my table. So what I can do now is, given my table, okay, I can solve for, and I didn't complete this for equilibrium. Let me move this around. It becomes X minus, oh gee willikers. That's not the erase mark. I can plug it into my calculated, somewhat given, KB expression and solve for X because I have all the components I need and I have one single common variable to solve for. So I get that KB is equal to 1.78 times 10 to the negative 5th, which is equal to the ion production. So it'd be the concentration of NH4 and OH minus. So that would be 3.616 times 10 to the negative 4th squared, because I'm just multiplying it by itself, basically. You'll have the same molarities. So when I plug it in, it'd be 3.16 times 3.16 squared, all over X minus 3.16 times 10 to the negative 4. And you can do some fun math, okay? And you would get that X is equal to 0.0059 molarity. And is that the correct sig figs? The answer is yes, because we were given a pH with only 2 decimals. So we know we have to report to 2 sig figs. Okay, 2 decimal pH, 2 sig figs. Okay, it's pretty much the exact same process. The only extra step here is this. Okay, this is where you differ in all of your K equilibrium problems. This is what's unique about a base, is it often requires you to do one more step. So that being said, and I'll put a little note, this is from the table, but for in your like math problems, you'd be given it. You'd be given K or a KB, okay, in a prompt. They would totally give it to you. Go ahead and try the next one. All right, so we just talked through it with the class, but hopefully the following the steps make sense. The only thing that was different about this problem was that you had to go past molarity and go to grams using molar mass and the specific volume that you diluted it in. Okay, so problem 3. Okay, problem 3 is you need to calculate KB given initial and pH or equilibrium values through pH. So again, this is like your dream problem because it's just plug and chug. Like there's no algebra really. There's no algebraic variable. It's just like figure out the numbers, plug it in, do the math. So for this problem, you were given a solution as prepared, dissolving 9.90 grams, okay, of the weak base hydroxylamine in enough water to produce 500 milliliters of the solution. The pH of the solution is found to be 9.904, 3 sig figs. Calculate the KB. Okay, so first and foremost, you are given initial, you're just given an initial molarity through a very roundabout way. You're told the grams. So in order to find the molarity of your original, what is this, hydroxylamine? Okay, writing the formula will be quicker. OH. Okay, it's going to equal moles over liters. So that's going to equal your grams, 9.90 grams, times your molar mass. Okay, so what's the molar mass of hydroxylamine? It is approximately 33 grams per mole. Okay, I'm not doing it perfectly, but 33 grams per mole. Whoa, sketchy. Moles, 33 grams. And then you're going to divide all of this by the liter value of 0.500 liters because you diluted it into a sample of 500 milliliters. Okay, and that's going to give you a concentration equal to 0.600 molarity. Okay, so you have your initial now. This is initial, right? Using the physics subscript. So you're then given your pH at equilibrium. The pH of the solution is at equilibrium. So your pH at equilibrium can then be used to figure out your pOH at equilibrium. If we set 14 minus pH at equilibrium, and we get a value of 14 minus 9.904, which is equal to 4.096. 4.096. And then using, of course, your pOH at equilibrium, you can find your OH concentration at equilibrium. And that's going to be equal to 10 raised to the pOH. So it's going to be equal to 8.0168 times 10 to the negative 5th molarity. Okay. And now what we do is we set up our information into the ICE table to calculate the complete equilibrium values and then plug into KB. So we go through and we say, well, I started off with, NH2OH plus water because we're trying to, again, isolate the behavior. And it's going to produce NH2OH2 plus and OH minus, okay? It would be the oxygen that most likely accepts that, just by the way, but it's possible for that. No, probably the oxygen. The end's pretty happy. So You set up your ice table. Okay. These are boom, boom, boom. And you are told the initial, which is you solve for it 0.660. You know, it's 0, 0. This, oh, well, you know the value, which is this is at equilibrium. Copy. So you just paste it in everywhere. Oh, make it tiny. Okay. Copy, paste, paste, and that's going to be added. So hold on, paste or subtracted. Right, paste, paste. Okay, so you know this is going to be subtracted, this is going to be added, this is going to be added, this is going to become 0.600 minus 8.0168 times 10 to the negative fifth. And you would get a value for that. Oh, I'm just going to go ahead and delete this and give you the value. Okay, it's going to give you the value of 0.59 repeated. Okay, is going to be that math that you can actually just solve for. And then you just plug into the KB expression. So you solve for, you say 8.0168. Your KB, of course, is the product of the ion concentration that you produce all over the initial reactant that you had, times 10 to the negative fifth. Well, it's going to be squared because it's going to be that times that. So that times itself to represent each ion produced all over 0.59 repeated if you actually put this into calculator. And it becomes a value of 1.707 times 10 to the negative eighth, which is a very small KB, which one aligns with the concept that you have a weak base in the first place. It's not producing a ton of ions. It's a low ratio. And that is your final answer. Okay, so I don't know about you, but I think that in order for tomorrow's lesson to work, you should, you know what? No, I'm going to require do this one on your own because tomorrow we have a lot of problems you have to get through. And I think it would be essential for us not to spend time doing a warm-up question that was too in-depth. So I want you guys to go ahead and just take 5 minutes to figure out this problem. And then we'll just check in with each other at the end, and then the class will be over. So let's talk about this one. It's following the similar process. You were given pH. So if you're given pH of solution, that means you know the acid present at equilibrium. If you know the acid present at equilibrium, so once you know the pH, you can calculate for POH. Once you know OH, you can calculate for equilibrium, concentration of OH minus. And you got a value of what? What'd you get a value of? Thank you. Does anyone else do these calculations? Okay, so Freya, what was yours? 0.0791 molarity. Okay. Okay, you guys can just speak up louder. Like you really can. Like, yeah. So once you know this, okay, you have the equilibrium. And if you have equilibrium of one, you can stoichiometrically figure out the equilibrium of the other ones, okay? You also need to use the initial, which you were given. So you just set up your ice table, okay? And I am going to ask that tomorrow that corner be divided into the 4 corners of this classroom. Okay. Huh? I am not talking to you. Oh, yeah, yeah. We're just going to split you up for just like a day. Okay. We might find that the ethos, just like when I split them up, is terrible, but just for one day, we're just going to split. Okay. So CH3, NH3. You know what? Maybe I should do a seating chart. Okay. And OH minus, okay? And then you set up your ice table. Yeah, I think I will, because honestly, I just hear Keaton's voice with the answers. I want to hear your guys' thoughts. And I want to hear what other people are thinking other than just these tennis boys. So I think that will be one of my new things for tomorrow. Indeed. Okay, so you then just plug in the values that you found. Well, you were told that you have a 0.400 molarity. Okay, and you know that you start with 0, 0. Okay. So you just do what we normally do. We take our equilibrium values. Oh God, what the? We take our equilibrium values and we plug them in stoichiometrically to our change in ice table. Okay, so if I can just get this without getting that. Copy, paste. Ah, geez. Okay, perfect. So, copy. Is that a thing? Oh, well, too late. Okay. Can someone do the math for me that shows what my equilibrium value for my acid would be? Lorena. 0.3205. And then you just simply plug into KB. And that's going to equal what? Craig.
0.019 or 0.02.
0.02 because are we only one sig fig?
Oh, my bad. Okay, so it is
19. That's it. No times 10 to the anything. Hey, this is the strongest, weakest that we've ever met so far in all of our practice problems. So now, as far as percent ionization works, all right, that's the KB. You know, I actually think percent calculator and percent ionization. So what you would do for percent ionization is you would do the concentration of the ion. Ooh, 0.791 all over the initial concentration, 0.400 times 100. And what do you guys get for this math? What was your percent ionization? The concentration of the base produced over the initial, or sorry, the OH minus base ion produced over the initial. What did we get? What? 19.8%. Great. You also, kind of depending on how this question was exactly, and I'm not exactly sure what this question was looking for, you also could have done the concentration of the initial over, or the concentration, not the concentration, the Ka value over the initial concentration. That would have also been another type of percent ionization if you did Ka over initial. Okay. Thank you so much. Have a great day.